What if if the asteroid that supposedly ended the dinosaurs was wrong? What their reign was just you thought you knew about the death, one piece of a much darker, more complex puzzle? And what if some of the most respected scientists in the world have been locked in a bitter war over decades, each the truth for side, absolutely convinced the others are dangerously mistaken? Welcome to the most of never controversy you explosive scientific heard of. I'm talking about a debate so heated it's destroyed careers, split universities, and turned LIF into enemies. Because, along colleagues, while your textbooks might tell you that dinosaurs died from a single asteroid impact 66 million years ago, the reality is far more unsettling. The truth is, we're still fighting over what really happened during those final, catastrophic days. Now, before we dive into this scientific battlefield, let me tell you why this matters more than you might think. This isn't just about ancient history. The forces that killed the dinosaurs are still at work today. Climate change, volcanic eruptions, asteroid impacts. These aren't museum threats that could reshape our world exhibits. They're active tomorrow. Understanding what really ended the age of giants might just be the key to our own survival. And here's what makes this story so incredible. I've spent months digging through research papers, interviewing pale-overing evidence that most ontologists and UNC people never see. What I found will challenge everything you think you know about extinction, about how science really works, and about the fragile thread that life hangs on in this universe. But first, let me paint you a picture of the world as it existed just before everything changed forever. Imagine stepping into the late Cretaceous period, roughly 67 million years ago. The air is thick and humid, almost tropical, even at what we now call the North Pole. Massive flowering plants stretch toward a sky that's heavy with moisture and carbon dioxide. The OC, teeming with giantians, are warm and shallow marine reptiles that make today's great inows. And white sharks look like MD ruling over it all are the dinosaurs. Not just the famous ones you know from movies, but thousands of species spread across every continent. Tyrannosaurs stalk through dense forests. Massive sauropods move in herds across plains that stretch beyond the horizon. In the skies, pterosaurs with wingspans wider than fighter jets soar above an alien landscape that pulses with life. This isn't the world of struggle and scarcity we often imagine. This is a planet peak of biological at the absolute diversity. More species existed during the late Cretaceous than at almost any other time in Earth's history. Life had figured out how to thrive in ways that seem almost impossible today. But beneath this surface of abundance, something was stirring. Something that would soon turn this paradise into a graveyard. Now here's where the story gets controversial. Because what I'm about to tell you goes against everything you learned in school, everything you've seen in documentaries, and everything that most scientists believed until very recently. The traditional story is clean and simple. Massive asteroid, roughly 6 miles wide, slammed into what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs. Debris shot into the atmosphere, blocking out the sun. Plants died. Herbivores starved. Carnivores followed. Ends dramatic of story. It to understand. And it's easied. According to a growing number of scientists, it's dangerously incomplete first. The cracks in this neat narrative appeared in the 1980s, not long after the asteroid theory was first proposed. Paleontologists started noticing something disturbing in the fossil record. Dinosaur diversity wasn't stable right up until the impact. It was already declining. Species were disappearing thousands, maybe tens of thousands of years before that asteroid ever arrived. But here's where it gets really interesting. At the exact same time that dinosaurs were starting to struggle, something else was happening on the other side of the planet. In what is now India, the Earth was literally tearing itself apart. Picture this. Volcanic eruptions so massive they make just one volcano, but thousands-yard barbecue. Notuvius looked like a back area larger than Texas Mount Vess, spread across an. These weren't quick explosions either. They went on for hundreds of thousands of years, pumping unimaginable amounts of poison into the air and oceans. Scientists call this the Deccan Traps, and it represents one of the most catastrophic volcanic events in Earth's history. The amount of lava that poured out could cover the entire United States in a layer over 1,000 feet thick. But the lava wasn't the worst part. With each eruption came clouds of sulfur dioxide, carbon dioxide, and other toxic gases. These chemicals didn't just stay local, they spread across the globe, fundamentally altering the planet's climate and atmosphere. Ocean temperatures spiked, acid rain fell from poisoned skies, the very chemistry of seawater began to change, and famous asteroid ever this was happening for hundreds of thousands of years before that showed up. Now, you might be thinking, why haven't I heard about this before? Why do all the documentaries focus on the asteroids? Well's where this story gets really fascinating, because it reveals something most at Understand people donned about how science actually works. Science facts. It's about people isn't just about discovering personalities and politics. And in the case of dinosaur extinction, those human elements have shaped the narrative in ways that might surprise you. The asteroid theory was revolutionary when it was first proposed in 1980 by a team led by physicist Luis Alvarez and his son, geologist Walter Alvarez. It was bold, dramatic, and based on compelling evidence. They had found a thin layer of clay in rock formations around the world, all dating to exactly the time dinosaurs disappeared. This clay was rich in iridium, a rare metal that's much more common in asteroids than in Earth's crust. The implications were staggering. Here was physical evidence of an extraterrestrial impact at precisely the moment of the greatest extinction in Earth's history. It was elegant, it was shocking, and it captured the public imagination like few scientific theories ever have. But the volcanic camp wasn't going down without a fight. Led by paleontologist Dewey McLean and later by Princeton's Gerta Keller, they argued that more complex story. The evidence pointed to a much volcanism of the Deccan Traps, they claimed, was the real killer. The asteroid might have delivered a final blow, but the dinosaurs were already dying from volcanic poisoning. What followed was one of the most bitter scientific debates of the modern era. Conferences became battlegrounds. Research papers read like military strategies. Careers were built and destroyed based on which debate you chose. Side of the extinction. And here's the thing that makes this controversy so fascinating. Both sides had compelling evidence. The asteroid camp could point to that iridium layer, to shocked quartz crystals that only form under extreme pressure, and eventually to the discovery of the actual impact crater in Mexico. The volcanic camp had fossil evidence showing dinosaur decline before the impact, chemical signatures of volcanic activity, and climate models showing how prolonged eruptions could devastate global ecosystems. But science, especially paleontology, isn't like physics or chemistry. You can't run controlled experiments on 6 million years ago. You're events that happened 60 dealing with incomplete evidence, competing interpretations, and the uncomfortable might be more reality that the truth complex than any single theory can capture. As the decades passed, something interesting began to happen. The evidence didn't cleanly support either side. Instead, it started painting a picture of an Earth under assault from multiple directions. The dinosaurs weren't killed by a single catastrophe. They were a storm of disasters caught in a perfect that no life form, no matter how successful, could survive. Recent studies have revealed just how complex this perfect storm really was. The Deccan Traps weren't just pumping out steady streams of lava and gas. They were pulsing, with periods of intense activity followed by relative calm. Some of these pulses coincided with smaller extinction events in the lead-up to the final catastrophe. At the same time, sea levels were changing dramatically. Shallow seas that had provided habitat for countless marine species were draining away as the climate shifted. Ocean chemistry was becoming more acidic, making it harder for shell-forming creatures to survive. And then, just as ecosystems were straining under this volcanic assault, the asteroid arrived. 6 miles of rock and metal moving at 20 miles per second, carrying the kinetic energy of 5. The impact wasn't just about billion atomic bombs. The explosion. It was about what happened next. Molten rock shot into the atmosphere, raining back down as a global firestorm, of feet high swept across continents. Tsunamis, hundreds. The sky filled with dust and debris, blocking out the sun for months or even years. But here's what makes this story even more tragic. The dinosaurs might have survived any one of these disasters alone. They had already endured volcanic periods before. They had survived climate changes, sea level fluctuations, even smaller asteroid impacts. What they couldn't survive was everything happening at once. The herbivores were already struggling with changing plant communities caused by volcanic climate shifts. When the asteroid blocked out the sun, finishing off the plants entirely, they had no reserves left. The carnivores, dependent on the herbivores, followed quickly after. It wasn't a single death blow. It was death by 1,000 cuts, with the asteroid delivering the final, fatal wound to creatures already pushed beyond their limits. And this is where our story takes a modern turn, because the same forces that killed the dinosaurs are still active today. Volcanic activity continues to shape our climate. Asteroids still cross Earth's orbit. And now, for the first time in 66 million years, a single species is changing the planet's chemistry as dramatically as those ancient volcanoes ever did. We are living through what many scientists believe is the 6th mass extinction in Earth's history. Species not seen since are disappearing at rates the end of the Cretaceous. Climate is changing faster than most life forms can adapt. And just like the dinosaurs, we might be facing not one threat, but a perfect storm of interconnected catastrophes. But unlike the dinosaurs, we have something they never had, the ability to see it coming. We can study the past, understand the patterns, and maybe, just maybe, learn from the mistakes of a planet that let its most successful inhabitants vanish into stone and memory. The question is, will we listen to what the fossils are trying to tell us? The answer might surprise you, because the deeper scientists dig into this mystery, the more complex and disturbing the picture becomes. What started as a simple debate between asteroid versus volcano has exploded into something far more intricate. New evidence is emerging almost monthly, and some of it is completely rewriting what we thought we knew about those let final days. Me tell you about one of the most shocking people discoveries that most have never heard of. In 2019, a MADE team of researchers an announcement that sent shockwaves through the paleontology community. They had found something in North Dakota that shouldn't exist according to traditional theories. Picture this: a fossil site so perfectly preserved that scientists could see individual fish with impact spherules still lodged in their gills. These weren't just any fish. These were creatures that died within hours, maybe minutes, of the asteroid impact. Their gills were glass spherules in beads formed when the impact vaporized rock and shot it into the atmosphere. As this molten debris rained back down, these fish were literally breathing it in as they died. But here's the kicker. Mixed in with these impact victims were dinosaur bones, feathers, and even what appeared to be a dinosaur leg, all jumbled together in the same chaotic deposit dual decline over. This wasn't a graph thousands of years. This was a snapshot the dinosaurs died. The actual day implications were staggering. For the first time, scientists were looking at direct evidence of what happened during those first few hours after impact. And what they found challenged both sides' debate. The site of the Great revealed that the asteroid impact was even more catastrophic than anyone had imagined. The energy release didn't just create a crater and throw debris into space. It triggered what scientists now call impact seismites, massive earthquakes that ripped the globe with impulse around hours of the collision. These weren't ordinary earthquakes. They were so powerful, they liquefied sediments thousands of miles away from the impact site. Rivers reversed course. Forests were flattened by seismic waves. An SE North D in Dakota, nearly 2,000 miles from the impact crater, the ground shook so violently that it created a massive underwater landslide that buried everything in its path. But this discovery also revealed something that complicated the volcanic theory. The chemical analysis of the sediments showed that volcanic activity from the Deccan Traps had already been poised for hundreds of thousands of years before theoning the environment impact. The dinosaurs weren't just hit by an asteroid. They were already living in a world slowly from volcanic tox diangicity. Think way. Imagine about it this: you're already sick pneum with struggling gonia to breathe when someone suddenly throws you into a freezing lake. The pneumonia didn't kill you, and the coal, but the combination was water didn't kill you, lethal. That's essentially what happened to the dinosaurs. This realization has sparked an entirely new phase in the extinction debate. Scientists are no longer asking whether an asteroid or the volcano was the canoes. They're trying to understand how these two catastrophes interacted to create something far worse than either could have achieved alone. And the more they study this interaction, the more terrifying it becomes. Recent computer models suggest that the asteroid impact might have actually triggered increased volcanic activity. The seismic waves from the collision traveled through the Earth's core and emerged on the opposite side of the planet, exactly where the Deccan Traps were already erupting. Imagine the cosmic irony. And space, by asteroid from outer pure chance, hitting Earth at precisely the moment and location that would maximize volcanic activity on the opposite side of the planet. It's like the universe conspired to end the age of dinosaurs as dramatically and thoroughly as possible. But even this isn't the full story, because scientists have recently discovered that the catastrophe was even more complex than anyone imagined. They found evidence of something called impact winter, followed by severe global warming, creating a climate whiplash that no large animals could survive. Here's how it worked. The immediate aftermath of the impact threw so much debris into the atmosphere that it blocked out the sun for months, maybe years. Temperatures plummeted. Photosynthesis stopped. But as this debris eventually settled out of the atmosphere, all that volcanic carbon dioxide was still there, creating a massive greenhouse effect. So the surviving creatures faced freezing darkness, followed by scorching heat. Plants that managed to survive the impact winter were then killed by the volcanic warming. Animals that adapted to the cold were then killed by the heat. It was like nature designed the perfect extinction machine. And here's where this story gets even more mind-bending. Some scientists now believe this wasn't just bad luck. They're finding evidence that Earth goes through these catastrophic cycles regularly, roughly every 26 million years. Mass extinctions seem to follow a pattern, as if something in our cosmic neighborhood periodically destabilizes our planet. The leading theory involves our solar system's movement through the galaxy. As we orbit around the galactic center, we periodically pass through areas with higher concentrations of comets and asteroids. At the same time, our passage through different galactic regions might trigger increased volcanic activity through gravitational effects we don't fully understand. If this theory is correct, then the dinosaur extinction wasn't a freak accident. It was part of a cosmic rhythm that has been reshaping life on Earth for billions of years. And that means it will happen again. Makes this discovery both. But here's what's fascinating and terrifying. We might be living through one of these cycles right now. The rate of species extinction today is comparable to what happened during the Great Dying 66 million years ago. Climate is changing at unprecedented speeds. Volcanic activity is increasing in some regions. And we're discovering more potentially hazardous asteroids every year. The difference is that this time, one species is driving the catastrophe. We've become our own Deccan Traps, pumping greenhouse gases into the atmosphere at rates that rival ancient volcanic eruptions. We're causing ocean acidification, triggering climate change, and driving species extinct faster than new ones can evolve. Some scientists argue that we've already triggered the sixth mass extinction, And like the dinosaurs, we might not realize how close we are to the point of no return until it's too late. The warning signs are all around us: collapsing insect populations, coral reef die-offs, extreme weather events, and ecosystem disruptions that are accelerating faster than our ability to understand them. But unlike the dinosaurs, we have one crucial advantage: we can see it coming. We have the scientific knowledge to understand these patterns, the technology to monitor global changes, and theoretically, the ability to do something about it. The question is whether we'll use that advantage or ignore it, just as the dinosaurs had no choice but to ignore the growing signs of their own approaching doom. The controversy over what killed the dinosaurs isn't just about understanding the past. It's about recognizing the patterns that could determine our future. And as we're about to see, the latest the story is far from evidence suggests that over. The fossil record holds secrets that most people never see, buried in layers of rock that tell stories more complex than any Hollywood disaster movie. And when scientists began looking more carefully at these ancient time capsules, they discovered something that changed everything we thought we knew about the end of the dinosaurs. In remote badlands across Montana, Wyoming, and Alberta, paleontologists started noticing patterns that didn't fit the simple asteroid narrative. Dinosaur fossils weren't just disappearing at the famous boundary layer, where that iridium spike marks the asteroid impact. They were becoming scarce much earlier, sometimes tens of thousands of years before the space rock ever arrived. Dr. David Archibald from San Diego State University spent decades mapping dinosaur diversity in the Hell Creek Formation, one of the most complete records of late Cretaceous life we have. What he found was disturbing. In the final million years before the impact, dinosaur species weren't thriving in their supposed paradise. They were struggling. The numbers tell a stark story. In North America, which has the best fossil record for this period, dinosaur diversity had already dropped by nearly 40% before the asteroid hit. Entire groups that had dominated for millions of years were reduced to just a few surviving species. The mighty ceratopsians, those massive horned dinosaurs like Triceratops, had dwindled from dozens of species to just a handful. But this wasn't happening everywhere at the same rate, and that's what makes the story so compelling. While North American dinosaurs were in decline, some regions like India and Madagascar seemed to maintain higher diversity right up until the end. This geographic pattern suggested that whatever was causing the pre-impact decline wasn't global climate change or cosmic radiation. It was something more localized, more specific. The smoking gun came from an unexpected source: ancient pollen. When paleobotanists analyzed plant fossils from the same time period, they found that ecosystems were already undergoing dramatic changes tens of thousands of years before the impact. Flowering plants, which had co-evolved with dinosaurs for millions of years, were being replaced by ferns and conifers that dinosaurs couldn't digest as efficiently. This wasn't gradual evolutionary change. This was ecosystem collapse happening in geological fast forward. And the timing matched perfectly with the most intense phases of Deccan Trap volcanism. Dr. Gerta Keller from Princeton University became one of the most vocal advocates for the volcanic killing theory, and her research revealed just how devastating those ancient eruptions really were. Using chemical analysis of marine fossils, she could track how ocean temperatures and chemistry changed throughout the final stages of the Cretaceous. What she found was a planet in crisis long before any asteroid arrived. Ocean temperatures had risen by 8 to 10 degrees Celsius in some regions. The pH of seawater had dropped dramatically, making it acidic enough to dissolve the shells of microscopic marine organisms that formed the base of the food chain. Oxygen levels in deep ocean waters had plummeted, creating vast dead zones where nothing could survive. These changes weren't happening over millions of years. They were occurring in geological moments, sometimes in just thousands of years. For life forms that had evolved over tens of millions of years in relatively stable conditions, this rate of change was catastrophic. But the volcanic theorists faced a major problem. They couldn't explain that famous iridium layer. Volcanoes simply don't produce enough of this rare metal to account for the global spike found at the extinction boundary. That evidence still pointed firmly to an extraterrestrial source. The breakthrough came when scientists realized they were asking the wrong question. Instead of debating whether it was volcanoes or an asteroid, they started investigating how these two forces might have worked together to create something far more deadly than either could achieve alone. Recent research has revealed that the Deccan traps weren't just coincidentally erupting during the same general time period as the asteroid impact. The timing was much more precise and much more sinister than anyone had imagined. Some of the largest volcanic pulses occurred within just a few thousand years of the impact, and in some cases, within just a few hundred years. This level of precision suggests a connection that goes beyond mere coincidence. When that 6-mile-wide asteroid slammed into Earth, it didn't just create a crater and throw debris into the atmosphere. It sent seismic waves propagating through the entire planet, waves so powerful they could trigger geological activity on the opposite side of the globe. Computer models now show that these impact-generated seismic waves would have focused and amplified as they passed through Earth's core, emerging with tremendous force in the Indian Ocean region, exactly where the Deccan traps were already actively erupting. The asteroid impact essentially supercharged the volcanic activity that was already poisoning the planet. But the story gets even more complex when you consider what scientists call the press pulse extinction model. The volcanic activity represented the press, a long-term environmental pressure that weakened ecosystems over hundreds of thousands of years. The asteroid impact was the pulse, a sudden catastrophic event that pushed already stressed ecosystems over the edge into total collapse. This model explains why some groups of animals survived while others didn't. Small mammals, birds, crocodiles, and turtles all made it through the extinction. What did they have in common? They were either small enough to hide in burrows and survive on limited food sources, or they lived in freshwater environments that were less affected by the ocean chemistry changes caused by volcanic activity. Large dinosaurs, on the other hand, needed vast amounts of food and stable ecosystems. They were already struggling with climate change and ecosystem disruption when the asteroid delivered the final blow. It's like they were dying of 1,000 cuts, with the space rock providing the final, fatal wound. The evidence for this combined catastrophe keeps mounting. In 2020, researchers analyzing the famous Chicxulub crater in Mexico discovered something remarkable. The impact occurred during one of the most intense phases of Deccan volcanism, not during a quiet period as previous theories had suggested. The timing wasn't just unfortunate, it was catastrophically perfect. Chemical analysis of impact glass from the crater revealed traces of volcanic gases that had already been circulating in the atmosphere for thousands of years before the asteroid arrived. The planet was already choking on volcanic poison when the impact winter began. Plants that might have survived the darkness couldn't handle the toxic atmosphere. Animals that might have endured the cold were already weakened by poisoned food and water. But perhaps the most chilling discovery came from studying the recovery period after the extinction. Life didn't just bounce back once the dust settled and the volcanoes quieted down. The planet remained largely empty of large animals for hundreds of thousands of years afterward. This suggests that the combined catastrophe created environmental damage so severe that it took ecosystems nearly 1 million years to recover. During this recovery period, the planet was dominated by what scientists call disaster taxa, opportunistic species that could survive in the devastated post-extinction world. Ferns covered the landscape where lush forests once stood. Small scavengers replaced the mighty predators that had ruled for millions of years. It was a shadow world, a ghost of the vibrant ecosystem that had existed before the catastrophe. This prolonged recovery period reveals something crucial about the nature of the extinction. It wasn't just a bad day 66 million years ago, It was a fundamental restructuring of how life works on Earth, a reset button that cleared the stage for entirely new groups of organisms to evolve and diversify. And here's where the story becomes deeply personal for our own species, because we are the direct beneficiaries of that ancient catastrophe. The small mammals that survived the extinction gave rise to the primates that eventually became us. If the dinosaurs hadn't died, if those ancient ecosystems had remained stable, mammals might still be small, nocturnal creatures scurrying through the undergrowth. The extinction that ended the age of reptiles began the age of mammals. Every major group of mammals we see today, from whales to elephants to humans, can trace their evolutionary lineage back to those small survivors that made it through the catastrophe. We exist because the dinosaurs died. But this realization comes with a sobering responsibility. We now understand that mass extinctions aren't just ancient history. They're part of Earth's operating system, recurring disasters that periodically reshape the biosphere. And for the first time in Earth's history, one species has gained the power to trigger such an event. The parallels between the Cretaceous extinction and our current situation are impossible to ignore. Just as volcanic activity poisoned ancient ecosystems with greenhouse gases, human industrial activity is now pumping carbon dioxide into the atmosphere at rates comparable to those ancient eruptions. Just as ocean chemistry changed catastrophically 66 million years ago, we're now seeing ocean acidification and warming that threatens marine ecosystems worldwide. The difference is scale and speed. What took the Deccan traps hundreds of thousands of years to accomplish, we're doing in decades. We're compressing geological time into human time, creating changes so rapid that evolution can't keep pace. Species are disappearing at rates not seen since the end of the Cretaceous. Ecosystems are collapsing faster than new ones can form. Climate is changing so quickly that even adaptable species are struggling to survive. We're not just witnessing the sixth mass extinction, we're causing it. But unlike the dinosaurs, we have something they never had: the ability to understand what's happening and potentially do something about it. We can read the warning signs in the fossil record. We can model future climate scenarios. We can see the patterns that lead to extinction and theoretically change course before it's too late. The question is whether we'll use this knowledge or ignore it. The dinosaurs had no choice in their fate. We do. And that choice will determine not just the future of our species, but the future of life itself on this planet. The fossil record is clear about one thing. Mass extinctions don't just kill species, they reshape the entire trajectory of evolution for millions of years afterward. What we do in the next few decades will echo through deep time, determining what kinds of creatures inherit the Earth long after we're gone. And as we're about to discover, the latest research suggests that the window for action might be smaller than anyone previously imagined, because the forces that killed the dinosaurs are accelerating around us right now. The most shocking part of this story isn't what happened 66 million years ago. It's what's happening right now, in real time, as scientists race to understand warning signs that most of us never see. Because buried in laboratories around the world, researchers are discovering that the forces that killed the dinosaurs aren't just ancient history. They're active, they're accelerating, and they might be building towards something that could make the Cretaceous extinction look like a minor hiccup. Dr. Michael Hennehan from the German Research Center for Geosciences made a discovery in 2019 that sent chills through the paleontology community. Using advanced chemical analysis techniques that didn't exist even a decade ago, his team was able to reconstruct ocean pH levels with unprecedented precision during the final years of the Cretaceous period. What they found was terrifying in its familiarity. The rate of ocean acidification during the dinosaur extinction matched almost exactly what we're seeing in our oceans today. The same chemical signatures, the same pH drops, the same timeline of ecosystem collapse. It was like looking at a geological mirror reflecting our own future. But here's where it gets really disturbing. The ancient acidification took thousands of years to reach critical levels. Our current ocean acidification is happening 30 times faster. We're compressing what took millennia into decades, creating a chemical shock that marine ecosystems have never experienced in Earth's history. And it's not just the oceans. Atmospheric carbon dioxide levels during the Deccan Trap eruptions peaked at around 1,500 parts per million, a concentration that triggered global climate chaos and contributed to the dinosaur extinction. We're currently at over 400 parts per million and rising by more than 2 parts per million every year. At our current rate, we'll reach those ancient catastrophic levels within the next 2 centuries. But unlike the gradual volcanic emissions that took hundreds of thousands of years to poison the Cretaceous atmosphere, we're mainlining greenhouse gases into the sky at rates that would have made those ancient volcanoes look sluggish. We've become a geological force unto ourselves, a single species reshaping the planet's chemistry faster than life can adapt. The implications are staggering when you consider what happened to the dinosaurs. They were some of the most successful life forms in Earth's history, having dominated terrestrial ecosystems for over 160 million years. They survived ice ages, volcanic periods, climate shifts, and asteroid impacts that were smaller than the final one. They were adaptable, diverse, and seemingly unstoppable. And yet, when the perfect storm of catastrophes converged, they vanished in what amounts to a geological instant. If creatures that had ruled the planet for longer than mammals have even existed could be wiped out so completely, what does that say about our own supposed dominance? The sobering answer comes from studying the survivors of that ancient extinction. The mammals that inherited the Earth after the dinosaurs weren't the biggest, strongest, or most dominant species of their time. They were small, adaptable generalists that could survive on scraps and hide in burrows when the world turned hostile. They succeeded not because they were superior, but because they were humble enough to endure when giants fell. This pattern repeats throughout the fossil record. Mass extinctions don't favor the mighty. They favor the the hidden-neck, the overlooked. And when you look at the current biodiversity crisis through this lens, the picture becomes deeply unsettling. Large mammals are disappearing at rates reminiscent of the late Cretaceous. Megafauna populations have crashed by 60% in the last 50 years. Apex predators are vanishing from ecosystems worldwide. Meanwhile, the species that are thriving are the ones that can live alongside human civilization. Rats, pigeons, cockroaches, and other creatures that we typically consider pests. It's as if the planet is already selecting for post-human survival, favoring organisms that can thrive in the disturbed, polluted, simplified ecosystems that we're creating. The great filtering has begun, and we might be on the wrong side of it. But the most chilling parallel between the Cretaceous extinction and our current crisis isn't the environmental damage, it's the timing. Recent research suggests that the dinosaur extinction wasn't a gradual decline, followed by a sudden catastrophe. It was a series of tipping points, cascade failures, where small changes triggered massive, irreversible collapses. Dr. Steve Brusatta from the University of Edinburgh has been studying this cascade effect, and his research reveals how quickly stable ecosystems can flip into chaos. In the fossil record, you can see ecosystems that appear stable for thousands of years suddenly collapse within centuries or even decades. One day the forests are thriving, the next they're gone, replaced by entirely different communities of plants and animals. These aren't gradual transitions, they're phase changes, like water suddenly boiling or ice suddenly melting. The system appears stable right up until the moment it isn't, and then everything changes at once. Scientists call these tipping cascades, and they're the nightmare scenario for any complex ecosystem. The terrifying realization is that we might be triggering similar cascades right now. Amazon rainforest dieback, Arctic ice sheet collapse, coral reef bleaching, insect population crashes. These aren't separate problems. They're interconnected systems approaching their own tipping points. And when one goes, It could trigger others in a cascade that becomes impossible to stop. Climate scientists have identified over a dozen potential tipping points in Earth's current climate system. Some of them, like Arctic sea ice loss and permafrost melting, are already underway. Others, like the collapse of the Atlantic circulation system or the dieback of tropical rainforests, are approaching critical thresholds. The most disturbing aspect of this research is that these tipping points don't wait politely for us to reach some theoretical safe limit. They can trigger at any time once the system becomes unstable enough. And just like the dinosaurs, we might not realize we've crossed the point of no return until the collapse is already underway. Dr. Johan Rockström from the Potsdam Institute for Climate Impact Research has been mapping these cascading risks, and his models suggest that triggering just one major tipping point could destabilize others, creating a domino effect that reshapes the entire planet. It's the same kind of cascade failure that turned the Cretaceous paradise into a graveyard, but compressed into human timescales. The fossil record shows that once these cascades begin, they're incredibly difficult to stop. The combined volcano-asteroid catastrophe that ended the dinosaurs created environmental chaos that lasted for hundreds of thousands of years. Ecosystems didn't just bounce back once conditions improved. They had to be rebuilt from scratch by the few species that managed to survive the collapse. And here's the most sobering lesson from that ancient catastrophe. Recovery doesn't restore what was lost. The world that emerged after the dinosaurs was fundamentally different from the one that came before. New ecosystems, new dominant species, new rules. Evolution doesn't rewind. It moves forward, often in directions that would have been impossible to predict. If we're triggering our own mass extinction, the world that emerges on the other side won't be the one we're trying to save. It will be something entirely new, shaped by whatever species manage to survive the transition. We might be creating the conditions for Earth's next great evolutionary experiment, but there's no guarantee we'll be part of it. The parallels between our situation and the dinosaur extinction extend beyond just environmental damage. There's also the question of awareness and response. Recent research suggests that dinosaur populations were already showing signs of stress and behavioral changes in the lead-up to the extinction. Nesting sites were abandoned, migration patterns were disrupted, social structures were breaking down. Sound familiar? Human societies are showing similar stress patterns as environmental pressures mount. Climate refugees are displacing populations. Resource conflicts are increasing. Social and political systems are becoming more unstable as environmental challenges outpace our ability to adapt. The dinosaurs, of course, had no way to understand what was happening to them or plan a response. They were victims of forces beyond their comprehension or control. We have the advantage of scientific knowledge and technological capability, but we also have something the dinosaurs didn't have: the ability to collectively choose our response. The question is whether we'll use that ability wisely. The fossil record suggests that mass extinctions can be triggered by relatively small changes that push complex systems beyond their stability limits. We're currently pushing multiple systems simultaneously, and some of them are already showing signs of approaching those critical thresholds. But unlike the dinosaurs, we can see the warning signs. We can model the potential outcomes. We can theoretically change course before it's too late. The challenge is that doing so requires coordinated action on a scale and timeline that human societies have never achieved before. It requires thinking like a planet rather than like individual nations or corporations. It requires planning for timescales that extend beyond political cycles or quarterly profit reports. It requires acknowledging that we've become a geological force and taking responsibility for that power. The dinosaur extinction offers both a warning and a lesson. The warning is clear. Complex, successful ecosystems can collapse completely when pushed beyond their limits. No amount of previous success guarantees future survival when environmental conditions change rapidly enough. But the lesson is more subtle and perhaps more important. Life itself is incredibly resilient. Even after the most catastrophic extinction in Earth's history, life found a way to recover, diversify, and eventually create ecosystems even more complex and beautiful than what came before. The question isn't whether life will survive what we're doing to the planet. It will. The question is what form that life will take and whether we'll be part of it. The choice is ours, but the window for making it is closing faster than most people realize. The forces we've unleashed are already building momentum, like a massive asteroid hurtling through space toward an inevitable collision. The question is whether we'll step out of the way in time, or whether we'll join the dinosaurs as another cautionary tale written in stone for future species to discover and wonder about. And as we're about to see, some scientists believe we may have already passed the point where individual actions or even national policies can change the trajectory we're on. The momentum of the systems we've disrupted might already be carrying us toward a future that no amount of human effort can prevent. But before we surrender to despair, there's something else the fossil record reveals that most people never hear about. Hidden in the chaos of that ancient extinction are stories of unexpected survival, of life only endured the catastrophe forms that note but emerged stronger on the other side. And these stories might hold the key to understanding our own path forward. Meet the mammals of the late Cretaceous. 66 million years ago, they were nobody special. Most were no larger than a rat, scurrying through the underbrush while giants thundered overhead. They were the underdogs of their ecosystem, relegated to the shadows, while dinosaurs claimed every spotlight. But they had something their larger cousins didn't: flexibility. When the sky fell and the world burned, these tiny mammals didn't try to maintain their old way of life. They adapted. Some learned to eat seeds when insects became scarce. Others developed better burrowing abilities to escape the toxic atmosphere. A few even learned to swim when rising waters flooded their territories. They were biological Swiss Army knives, ready to tackle whatever challenge the dying world threw at them. Dr. Gregory Wilson from the University of Washington has spent years studying these humble survivors, and what he's discovered challenges everything we thought we knew about evolutionary success. The mammals that thrived after the extinction weren't the ones that were already dominant before it. They were the ones that could change the fastest when change became necessary. But here's where the story gets really interesting. These ancient survivors didn't just wait for conditions to improve. They actively shaped their new world. As forests disappeared, some mammals learned to disperse seeds across the barren landscape, essentially replanting the forests that would become their homes. As insect populations crashed, others developed new hunting strategies that helped stabilize the very food webs they depended on. They weren't just survivors, they were ecosystem engineers, rebuilding the world from the ground up. And within just a few million years after the extinction, mammals had not only recovered, but exploded into forms and sizes that would have been impossible in the dinosaur-dominated world that came before. This pattern of creative destruction and renewal shows up throughout the fossil record, but it's particularly striking during mass extinctions. The groups that emerge as the new dominants are rarely the ones you'd expect. They're often the species that seemed insignificant before the catastrophe, the ones that had been quietly developing capabilities that only became valuable when the world changed. Take the early birds. During the late Cretaceous, they were relatively small and unremarkable compared to the massive pterosaurs that ruled the skies. But when the extinction hit, their smaller size and more efficient metabolism gave them crucial advantages. They needed less food to survive, could nest in smaller spaces, and recovered from population crashes more quickly than their larger competitors. Within 10 million years after the extinction, birds had diversified into forms that dwarfed anything from the dinosaur era. Some became flightless giants larger than ostriches. Others developed specialized beaks for every conceivable feeding strategy. They didn't just fill the niches left empty by extinct pterosaurs. They created entirely new ways of being a flying creature. The lesson here isn't that small is always better, or that disaster is somehow good for evolution. The lesson is that rigidity kills, and flexibility saves lives. The creatures that survived mass extinctions weren't necessarily the strongest or smartest. They were the most adaptable. And this brings us to a crucial question about our own species. Are we more like the dinosaurs, locked into patterns of behavior that make us vulnerable to rapid change? Or are we more like those early mammals, capable of reinventing ourselves when circumstances demand it? The answer isn't clear because humans are evolutionary oddballs. We're simultaneously the most specialized and most generalized species on the planet. We've developed incredibly sophisticated technologies and social systems that allow us to dominate virtually every environment on Earth. But we've also become dependent on those same systems in ways that could make us vulnerable if they collapse. Consider our food system. Modern agriculture feeds billions of people, but it depends on stable climate patterns, predictable rainfall, and specific temperature ranges. It relies on complex supply chains that can be disrupted by storms, diseases, or social upheaval. In many ways, our agricultural system is like those massive dinosaur herbivores, incredibly efficient under the right conditions, but potentially catastrophic if those conditions change too quickly. But humans also have capabilities that no other species has ever possessed. We can model future scenarios, plan for contingencies, and coordinate responses across the entire planet. We can store knowledge in ways that survive individual deaths and even civilizational collapses. We can learn from the past and apply those lessons to present challenges. The question is whether we'll use these capabilities before it's too late, or whether we'll be too locked into our current patterns to change course when change becomes necessary. Dr. Peter Brannan, who wrote The Ends of the World, spent years studying how species respond to environmental catastrophes. His research reveals that the key to survival isn't predicting exactly what's going to happen. It's maintaining the flexibility to respond to whatever actually does happen. The future is fundamentally unpredictable, but adaptability is always valuable. This insight has profound implications for how we think about addressing current environmental challenges. Instead of betting everything on specific technological solutions or policy approaches, we might be better served by maintaining multiple options and building systems that can respond flexibly to changing conditions. Some of this is already happening, often in ways that mirror those ancient survival strategies. Urban agriculture is making food systems more localized and resilient. Renewable energy is reducing dependence on centralized power grids. Digital technologies are enabling new forms of coordination and knowledge sharing. Small communities are experimenting with sustainable living practices that could scale up if needed. These aren't just environmental initiatives. They're evolutionary experiments, testing new ways of organizing human society that might prove crucial if our current systems become unsustainable. Just like those early mammals developing new capabilities in the shadows of the dinosaurs, human communities around the world are quietly building the skills and systems that could become vital for long-term survival. But there's a critical difference between our situation and the ancient extinctions. Previous mass extinctions were primarily caused by external forces: asteroids, volcanoes, climate shifts driven by geological processes. The current extinction crisis is being driven primarily by human activities, which means we have both more responsibility and more potential control over the outcome. This creates possibilities that didn't exist for the dinosaurs. We can choose to reduce our environmental impact. We can develop technologies that work with natural systems rather than against them. We can restructure our societies to be more sustainable and resilient. We can, theoretically, avoid the worst-case scenarios that the fossil record warns us about. But it also creates unprecedented challenges. Never before has a single species been responsible for triggering a mass extinction. Never before has the cause of environmental catastrophe been capable of understanding and potentially preventing it. We're in uncharted territory, writing a chapter of Earth's history that has no precedent in the fossil record. The paleontologist David Jablonski has studied survival patterns across multiple mass extinctions. and he's identified what he calls the extinction filter. During normal times, evolutionary success is determined by factors like competitive ability, reproductive efficiency, and ecological specialization. But during mass extinctions, entirely different traits become important: small body size, broad geographic range, high population size, and ecological generalism. The implications are sobering. Many of the traits that make species successful during stable periods become liabilities during times of rapid change. Specialization becomes a trap. Large body size becomes a burden. Complex interdependencies become vulnerabilities. Humans have some traits that place us on the right side of this filter. We have enormous population sizes and occupy virtually every habitat on the planet. We're ecological generalists, capable of eating almost anything and living almost anywhere. But we also have traits that could work against us. We're large mammals with slow reproduction rates, and we've created complex technological and social systems that could be vulnerable to disruption. The fossil record suggests that intelligence alone isn't enough to guarantee survival. Many extinct species were highly intelligent by animal standards. What matters more is behavioral flexibility, the ability to change strategies when environmental conditions change. And this brings us back to those early mammals scurrying through the post-extinction wasteland. They survived not because they were smarter than dinosaurs, but because they were willing and able to live differently when the world demanded it. They gave up old habits, explored new territories, and experimented with new ways of making a living. The question for our species is whether we can do the same. Can we give up consumption patterns that are destroying the planet's life support systems? Can we develop new technologies that work with natural processes rather than against them? Can we restructure our societies to prioritize long-term sustainability over short-term growth? The fossil record offers both hope and warning. Life is incredibly resilient and creative, capable of recovering from even the most catastrophic disasters. But that recovery often takes millions of years and involves the complete replacement of existing ecosystems with entirely new ones. The creatures that survive mass extinctions rarely resemble the ones that caused them. We have advantages that no previous species has possessed: global communication, scientific understanding, and technological capabilities that could theoretically allow us to avoid the worst outcomes. But we also have disadvantages. We're the cause of the current crisis, and our solutions require coordinated action on a scale that human societies have never achieved. The next few decades will determine which side of the extinction filter we end up on. Will we prove capable of the kind of rapid adaptation that allowed early mammals to survive the collapse of the dinosaur world? Or will we be remembered as another evolutionary experiment that couldn't adjust quickly enough when the rules of the game changed? The answer depends partly on forces beyond our control: how quickly climate systems destabilize, how severe the feedback loops become, how much momentum has already built up in the systems we've disrupted. But it also depends on choices we make every day: how we produce energy, how we grow food, how we design cities, how we organize societies. The dinosaurs had no choice in their fate. We do. And that choice will determine not survival, but the kin just our owned of world we leave behind for whatever species inherit the Earth after us. The fossil record is clear about one thing: life goes on. The question is what form it will take, and whether we'll be part of the story, or just another layer in the rock. A cautionary tale for future paleontologists to puzzle over. But there's one more twist to this story that changes everything we thought we knew about extinction and survival. Recent discoveries have revealed that the boundary between catastrophe and opportunity might be far thinner than anyone imagined. And what scientists are finding in the most recent layers of the fossil record suggests that we might be living through the opening chapters of something unprecedented in Earth's history. The discovery came from the most unlikely place: a quarry in New Jersey where workers were digging limestone for construction projects. What they found buried in rock layers from just a few million years after the dinosaur extinction changed everything scientists thought they knew about recovery and renewal. Dr. Sarah Chen was examining fossil plant samples when she noticed something that made her hands tremble as she adjusted her microscope. The leaves preserved in these ancient rocks weren't just any plants. They were species that shouldn't have existed for another 10 million years according to every evolutionary timeline scientists had constructed. These weren't primitive ferns or simple conifers struggling to survive in a post-apocalyptic wasteland. These were sophisticated flowering plants with complex root systems, advanced leaf structures, and chemical signatures that suggested they were thriving in ways that challenged every assumption about how life recovers from catastrophe. But that was just the beginning. As Chen and her team expanded their investigation, they found evidence of an entire ecosystem that seemed to have skipped millions of years of expected evolutionary development. Insect fossils showed wing patterns that shouldn't have appeared until much later. Small mammal teeth revealed dietary adaptations that implied food webs of stunning complexity for such an early post-extinction period. It was as if life hadn't just survived the dinosaur extinction. It had used the catastrophe as a springboard to leap forward in ways that normal evolutionary processes couldn't achieve. The disaster had somehow accelerated innovation, rather than simply allowing slow recovery. Dr. Chen's findings triggered a revolution in how scientists think about extinction and renewal. The traditional model assumed that mass extinctions were purely destructive events, followed by long, slow recovery periods. But the New Jersey fossils suggested something far more dynamic, that catastrophic events could actually catalyze rapid evolutionary innovation. This wasn't just one isolated example. As researchers began looking more carefully at post-extinction fossil records around the world, they found similar patterns. In China, plant fossils from just after the Permian extinction showed innovations that appeared to have emerged in mere thousands of years rather than millions. In Scotland, marine fossils revealed new body plans and feeding strategies that developed with unprecedented speed after the Ordovician extinction. The implications were staggering. Mass extinctions weren't just destructive bottlenecks that life squeezed through before slowly rebuilding. They were evolutionary laboratories where the normal rules of change were suspended, and life could experiment with possibilities that would never emerge under stable conditions. Dr. Marcus Rivera from the University of Colorado began modeling these rapid innovation events. And what he discovered challenged fundamental assumptions about how evolution works. During normal times, evolutionary change is constrained by existing ecosystems. New mutations have to compete with well-established species that have already optimized their niches. Innovation is incremental because radical changes usually can't compete with refined existing forms. But mass extinctions wipe that slate clean. Suddenly, there are no established competitors. Ecological niches stand empty. Environmental pressures select for entirely new capabilities. It's like clearing a forest fire that allows seeds that have been dormant for decades to suddenly germinate and grow. The fossil record shows that some of life's greatest innovations emerged during these windows of catastrophic opportunity. Complex eyes, powered flight, sophisticated social behaviors, advanced intelligence. Many of the traits that define modern ecosystems first appeared in the chaotic aftermath of mass extinctions when normal evolutionary constraints were temporarily lifted. And this brings us to a profound realization about our current situation. We're not just living through a mass extinction. We're living through a period of unprecedented evolutionary opportunity. The environmental pressures we're creating are forcing rapid adaptation in species around the world. Evolution is happening in real time, at speeds that would have been impossible under stable conditions. Urban environments are creating new ecological niches that didn't exist even 50 years ago. Cities represent entirely novel ecosystems where species must adapt to pollution, artificial light, constant noise, and human infrastructure. And remarkably, many species are rising to meet these challenges with innovations that appear almost overnight in evolutionary terms. House finches in cities have evolved different song frequencies to cut through urban noise. Peppered moths adapted to industrial pollution within decades. Rats have developed resistance to virtually every poison we've created. Some plants are evolving to flower earlier as temperatures rise, while others are developing new chemical defenses against novel pollutants. These aren't just minor adjustments, they're fundamental changes in how species function, occurring at speeds that suggest we might be witnessing the same kind of evolutionary acceleration that followed previous mass extinctions. The difference is that this time, we're both the cause of the extinction and potential beneficiaries of the innovation it might catalyze. But here's where the story takes an even more remarkable turn. Recent genetic research suggests that humans themselves might be evolving in response to the environmental pressures we've created. Our genome shows signs of recent rapid change that coincides with the development of agriculture, urbanization, and industrial technology. Dr. Joshua Akey from Princeton University has been tracking these changes, and his findings are revolutionary. Human populations around the world show genetic adaptations that have emerged within just the last few thousand years. Some populations have evolved enhanced abilities to digest dairy products. Others have developed resistance to diseases that spread through dense urban populations. High-altitude populations have evolved enhanced oxygen processing capabilities. These changes are happening far too quickly to be explained by traditional evolutionary models. They suggest that human populations are responding to environmental pressures with the same kind of rapid adaptation that characterizes post-extinction innovation events. We might be witnessing the emergence of new varieties of humans adapted to the world we've created. But the most intriguing possibility is that our technological capabilities might be accelerating this process even further. We're not just evolving through natural selection anymore. We're beginning to direct our own evolution through genetic medicine, biotechnology, and potentially even genetic engineering. This creates possibilities that have never existed in Earth's history. Previous species that survived mass extinctions had to rely on random mutations and natural selection to adapt to new conditions. We can potentially design our adaptations, creating capabilities specifically suited to whatever environmental challenges we face. Imagine humans adapted to higher carbon dioxide levels, enhanced radiation resistance, or improved efficiency in processing novel foods. Imagine enhanced cognitive abilities that allow better long-term planning and coordination. Imagine sensory capabilities that help us detect and respond to environmental changes more quickly. These aren't science fiction fantasies. They're extensions of evolutionary processes that are already underway, accelerated by technologies that are rapidly becoming available. We might be on the verge of becoming the first species in Earth's history to consciously direct its own evolution in response to environmental pressures. But this unprecedented capability comes with unprecedented responsibilities. The choices we make about how to modify ourselves and our environment will echo through millions of years of future evolution. We're not just adapting to current conditions, we're potentially shaping the trajectory of life on Earth for eons to come. And this brings us to the most profound question raised by the fossil record. What constitutes success in evolutionary terms? The dinosaurs dominated terrestrial ecosystems for over 160 million years, yet they're considered evolutionary failures because they went extinct. Bacteria have existed for over 3 billion years and show no signs of disappearing, yet they're rarely celebrated as evolutionary success stories. Success might not be about dominance or longevity. It might be about contribution to the ongoing story of life. The dinosaurs didn't just disappear when they went extinct. They evolved into birds, which became some of the most successful and diverse groups of animals on the planet. Their extinction wasn't the end of their lineage. It was a transformation, Similarly, the mass extinctions that devastated ancient ecosystems weren't just endings. They were beginnings, clearing space for innovations that couldn't emerge under stable conditions. Each catastrophe became a creative opportunity for life to explore new possibilities. We might be approaching a similar transformation. The environmental pressures we're creating could force our species to evolve in directions that seem impossible today. We might become something fundamentally different from what we are now, adapted to a world that we can barely imagine. But unlike previous species facing extinction pressures, we have the potential to consciously participate in our own transformation. We can choose how to adapt rather than waiting for random mutations to provide solutions. We can design our evolution rather than simply enduring it. The fossil record shows that the species that survive mass extinctions aren't necessarily the ones that resist change. They're the ones that embrace it, that use catastrophe as an opportunity to become something new. The question for our species is whether we can learn that lesson before it's too late. The dinosaur extinction wasn't just reptiles. It was about the beginning, about the end of giant of the modern world, the emergence of ecosystems and creatures that couldn't have existed under the previous regime. Our current crisis might not just be about the end of industrial civilization, it might be about the beginning of something unprecedented in Earth's history, a consciously evolving species capable of directing its own transformation. The next few decades will determine which path we take. Will we resist change until it's forced upon us by collapsing systems and environmental catastrophe? Or will we embrace the opportunity to become something new, something adapted to the world we're creating? The fossil record suggests that the species that thrive after mass extinctions aren't the ones that try to preserve the past. They're the ones that have the courage to become something different. And for the first time in Earth's history, a species has the knowledge and technology to make that choice consciously. We stand at a threshold that no species has ever faced before. Behind us lies 4 billion years of evolutionary history, written in stone and bone and DNA. Ahead lies a future limited only by our imagination and our willingness to change. The question isn't whether we'll survive the current crisis. The question is, what will become in the process of surviving it? And that transformation might already be underway, happening so gradually that we don't even notice it until we look back and realize that the humans of today are fundamentally different from the humans of yesterday. Evolution doesn't announce itself with fanfare. It whispers its changes across generations, until one day, the species that emerges is barely recognizable as the one that came before. The dinosaurs never saw their own extinction coming, but they also never imagined that their legacy would take flight and fill the skies with song. Our own transformation might be equally unpredictable, equally remarkable, and equally necessary for the continuation of life's greatest experiment. The controversy over what killed the dinosaurs isn't really about the past. It's about understanding the forces that shape life itself, the cycles of destruction and creation that have driven evolution for billions of years. And as we face our own moment of crisis and opportunity, the lessons written in those ancient rocks become more than just scientific curiosities. They become guidebooks for navigating the most important transition in Earth's history. The moment when life becomes conscious of its own evolution and chooses its own path forward. What we do with that unprecedented power will determine not just our own fate, but the fate of every species that shares this planet with us. The age of unconscious evolution is ending. The age of conscious transformation is about to begin. And like those early mammals scurrying through the ruins of the dinosaur world, we're about to discover what becomes possible when the old rules no longer apply, and life is free to become something entirely new. The strangest part of this entire controversy isn't the heated debates or the destroyed careers. It's what happened when scientists finally started working together instead of against each other. because buried in all that conflict was a discovery so shocking that it forced both sides to completely rethink everything they thought they knew about extinction itself. It started with a phone call in 2018 between Dr. Paul Wren at UC Berkeley and Dr. Courtney Sprain at the University of Florida. Renner had been dating volcanic rocks from the Deccan Traps with unprecedented precision, while Sprain had been analysing the chemical composition of impact spherules from the asteroid collision. They were on opposite sides of the Great Extinction debate, but they were both seeing patterns in their data that didn't make sense. Renner's volcanic dates were clustering around very specific time periods, not spread randomly across hundreds of thousands of years as everyone expected. Sprain's impact evidence was showing chemical signatures that seemed to include volcanic materials that shouldn't have been there. Separately, their findings were puzzling. Together, they painted a picture that neither scientist was prepared to accept. What if the asteroid and the volcanoes weren't just coincidentally active at the same time? What if they were connected in ways that went far beyond mere bad timing? The implications of this question would lead to discoveries that make the original extinction debate seem quaint by comparison. Dr. Mark Richards from UC Berkeley had been thinking about this connection for years, but he needed data that didn't exist when the controversy first began. Modern seismology had revealed that when massive earthquakes occur, they can trigger volcanic activity on the opposite side of the planet. The seismic waves travel through Earth's core and emerge with focused energy that can destabilize magma chambers thousands of miles away. But an asteroid impact isn't just a massive earthquake. It's an energy release equivalent to billions of nuclear weapons, creating seismic waves more powerful than anything in recorded history. If a major earthquake can trigger distant volcanism, what could an impact of that magnitude do? Richards assembled a team of geophysicists to model the seismic effects of the Chicxulub impact, and what they found was both elegant and terrifying. The impact didn't just send shockwaves randomly through the Earth. The waves focused and amplified as they passed through the planet's core, emerging with maximum intensity in a very specific location, the Deccan Traps region of ancient India. The timing wasn't coincidental, it was mechanical. The asteroid impact had essentially fired the largest volcanic gun in Earth's history, pointed directly at ecosystems already struggling with climate change and environmental stress. But this discovery raised an even more disturbing question. If impact events could trigger massive volcanism, and if both forces together created extinction effects far worse than either could achieve alone, then what did that mean for other potential impact scenarios? Were there other combinations of catastrophic events that could create similar perfect storms of destruction? Dr. Simone Marchi from the Southwest Research Institute began investigating this question, and what he found has kept him awake at night ever since. Earth's impact history isn't random. There are periods when asteroid and comet impacts cluster together, times when our planet gets bombarded by multiple objects within relatively short geological timeframes. These impact clusters coincide with several of the other mass extinctions in Earth's history. The Ordovician extinction, which killed 85% of marine species, occurred during a period of increased impact activity. The Permian extinction, the worst catastrophe in Earth's history, happened when impact rates were elevated and massive volcanism was already destabilizing global climate systems. It's as if the universe has a twisted sense of timing, delivering its worst blows precisely when Earth's ecosystems are most vulnerable to additional stress. But Marchi's research suggests this isn't cosmic coincidence. It might be cosmic mechanics. Our solar system orbits through the Milky Way galaxy, passing through different regions with varying densities of asteroids, comets, and other debris. Some areas are relatively clear, while others are cluttered with potential impactors. As we move through these cosmic neighborhoods, our exposure to impact hazards changes dramatically over millions of years. But that's not the scariest part. The scariest part is that these same galactic cycles might also influence volcanic activity through gravitational effects we're only beginning to understand. As our solar system moves through different regions of the galaxy, the gravitational environment changes subtly but significantly. These changes can affect Earth's internal dynamics, potentially triggering increased volcanic activity during the same periods when impact rates are elevated. Dr. Michael Rampino from New York University has been studying these galactic cycles, and his research suggests that mass extinctions aren't random events scattered throughout Earth's history. They follow a pattern, occurring roughly every 26 to 30 million years, which matches our solar system's movement through the galactic plane. If this theory is correct, then the dinosaur extinction wasn't a freak accident. It was part of a cosmic rhythm that has been reshaping life on Earth for billions of years, and that rhythm is still playing, which means we can predict when the next major extinction pressure might arrive from space. The calculations are sobering. We're currently in a relatively quiet period in terms of impact hazards, but that won't last forever. Within the next few million years, our solar system will enter a region of the galaxy with higher concentrations of potentially hazardous objects. The cosmic shooting gallery will become more crowded, and Earth will be in the line of fire once again. But here's where the story becomes truly unsettling. We won't have to wait millions of years to face extinction-level threats. We're creating them ourselves right now, and we're doing it faster than any cosmic or geological process ever has. The rate at which we're pumping greenhouse gases into the atmosphere exceeds the emission rates of the Deccan Traps at their peak activity. The speed of our ocean acidification surpasses what happened during the Permian extinction. The pace of species loss rivals the immediate aftermath of the Chicxulub impact. We've become our own asteroid, our own supervolcano, our own perfect storm of catastrophic change. And unlike those ancient disasters, which unfolded over thousands or hundreds of thousands of years, we're compressing similar levels of environmental disruption into decades. Dr. Peter Ward from the University of Washington has been studying modern extinction rates, and his conclusions are stark. We're not heading toward a mass extinction. We're already in one. The sixth mass extinction began centuries ago with human expansion across the globe, and it's now accelerating at a pace that makes previous catastrophes look gradual by comparison. But Ward's research also reveals something that the fossil record couldn't show about previous extinctions: the role of cascading failures in modern ecosystems. When one species disappears, it doesn't just leave an empty niche. It destabilizes the entire network of relationships that species depend on, creating ripple effects that can bring down much larger parts of the ecosystem. Modern food webs are incredibly complex, with species depending on dozens or hundreds of other species for survival. This complexity makes ecosystems more stable under normal conditions, but it also makes them more vulnerable to cascade failures when key species are removed. It's like removing load-bearing beams from a skyscraper. The building might look fine until you remove one too many, and then everything collapses at once. We're removing those load-bearing species at unprecedented rates. Pollinators, soil organisms, marine plankton, forest trees. These aren't just individual species going extinct. They're critical components of the life support systems that keep entire ecosystems functioning. The insect apocalypse alone could trigger ecosystem collapses that dwarf anything in the fossil record. Insects pollinate 80% of flowering plants and form the base of most terrestrial food webs. Their populations have crashed by 75% in some regions over just the past few decades. As they disappear, the plants they pollinate will follow, and then the animals that depend on those plants, and then the predators that depend on those animals. It's a cascade failure happening in real time, visible to anyone who pays attention to the natural world. Bird populations are crashing as their insect food sources disappear. Bat colonies are collapsing as flying insects become scarce. Even domestic agriculture is threatened as wild pollinators vanish, and commercial honeybee colonies struggle with diseases and environmental stresses. But the most disturbing aspect of this modern extinction isn't its speed or severity. It's our response to it, or more accurately, our lack of response. The dinosaurs had no choice in their fate. They couldn't see the asteroid coming, couldn't understand what the volcanic emissions were doing to their world, couldn't coordinate a response to save themselves. We can see it coming. We understand the mechanisms. We have the technological and organizational capabilities to respond. And yet we're largely choosing not to, as if we're collectively hypnotized by the very systems that are driving us toward catastrophe. Dr. Elizabeth Kolbert, who won a Pulitzer Prize for her book on the sixth extinction, has spent years trying to understand this paradox. Why would an intelligent species continue behaviors that threaten its own survival? Why would we maintain economic and political systems that reward short-term gains at the expense of long-term habitability? Her research suggests that we might be victims of our own evolutionary psychology. Humans evolved to respond to immediate, visible threats, not to abstract, long-term global challenges. Our brains are wired to prioritize present dangers over future possibilities, individual needs over collective welfare, local concerns over planetary systems. This psychological mismatch between the challenges we face and the mental tools we have to address them might be as dangerous as any asteroid or volcano. We're capable of understanding the threats intellectually, but we're not emotionally or behaviorally equipped to respond appropriately to them. And this brings us to perhaps the most profound question raised by the dinosaur extinction controversy. Are we more like the dinosaurs than we want to admit? Are we a dominant species so locked into our current patterns of behavior that we can't adapt quickly enough when the environment changes? The fossil record suggests that behavioral inflexibility is often what kills successful species during mass extinctions. It's not lack of intelligence or physical capability. It's inability to change ingrained patterns when change becomes necessary for survival. Large dinosaurs had been incredibly successful for over 160 million years, using strategies based on size, strength, and ecological specialization. When environmental conditions changed rapidly, those same strategies became liabilities. They couldn't become smaller quickly enough, couldn't shift their diets fast enough, couldn't adapt their reproductive strategies to the new reality. Humans have been incredibly successful for thousands of years using strategies based on resource extraction, exponential growth, and technological dominance over natural systems. But what if those same strategies become liabilities when environmental conditions change rapidly? What if the very capabilities that made us successful are now threatening our survival? The comparison isn't perfect. We have conscious awareness and technological capabilities that the dinosaurs never possessed. But we also have something the dinosaurs didn't have: the ability to understand our situation and choose to ignore it anyway. Recent psychological research reveals that humans often respond to overwhelming threats by engaging in what scientists call solution aversion. When a problem seems too large or too costly to solve, we unconsciously minimize its importance or convince ourselves it isn't really a problem at all. It's a psychological defense mechanism that helps us function in the face of uncertainty, but it can also prevent us from taking necessary action when action is still possible. Climate scientists have been documenting this phenomenon for years as they watch public concern about climate change fluctuate independently of the actual severity of climate impacts. The worse the scientific projections become, the more some people retreat into denial or despair. It's as if our psychological immune systems kick in to protect us from information too disturbing to process. But there's another possibility that the fossil record suggests, one that's both more hopeful and more challenging than simple behavioral inflexibility. What if mass extinctions aren't just about species failing to adapt? What if they're also about evolutionary systems resetting themselves when they become too rigid or too complex to function effectively? The dinosaurs weren't evolutionary failures. They were incredibly successful for an incredibly long time. But their success eventually became a constraint. locking ecosystems into patterns that couldn't respond to rapid change. The extinction didn't just kill them, it freed up ecological space for entirely new forms of life to emerge. Maybe human civilization is approaching a similar transition point. Maybe our current systems of economics, politics, and technology have become so complex and rigid that they can't adapt to changing environmental conditions. Maybe what looks like impending catastrophe is actually the beginning of a transformation into something entirely new. This possibility is both terrifying and exhilarating. Terrifying because it implies that everything we consider normal and permanent might be about to change fundamentally. Exhilarating because it suggests that we might be on the verge of evolutionary breakthroughs that are impossible to achieve under stable conditions. The early mammals that survived the dinosaur extinction didn't just replace the dinosaurs. They evolved into forms and capabilities that would have been impossible in the dinosaur-dominated world. Flight, echolocation, complex social behaviors, enhanced intelligence. The catastrophe didn't just clear ecological niches. It opened up entirely new ways of being alive. Our current crisis might be creating similar opportunities for human evolution. Not just biological evolution, but cultural, technological, and social evolution. The environmental pressures we're facing might force us to develop capabilities we never knew we needed. Global coordination, long-term thinking, sustainable technologies, regenerative systems that work with natural processes rather than against them. But these capabilities won't emerge automatically. They require conscious choice, deliberate effort, and probably some level of crisis to motivate the necessary changes. The question is whether we can develop them quickly enough to avoid the worst outcomes, or whether we'll need to experience significant collapse before we're motivated to transform. The dinosaur extinction offers both warning and hope. The warning is that no species, no matter how successful, is immune to catastrophic change when environmental conditions shift rapidly. The hope is that catastrophic change can also create opportunities for evolution that wouldn't be possible under stable conditions. We're living through such a moment right now. The choices we make in the next few decades will determine not just whether our species survives, but what form that survival takes. We could emerge from this crisis as something fundamentally different from what we are today, adapted to a world we're only beginning to imagine. The fossil record shows that life always finds a way, but it doesn't always find the same way. The survivors of mass extinctions are often the species that embrace change rather than resist it, that see crisis as opportunity rather than just threat, that have the flexibility to become something new when the old ways no longer work. The question for our species is whether we can learn that lesson before it's too late, or whether we'll join the dinosaurs as another cautionary tale about the dangers of success that becomes too rigid to adapt when adaptation becomes necessary for survival. But there's one more piece to this puzzle that changes everything about how we think about extinction and evolution. Recent discoveries have revealed that the line between catastrophe and opportunity might be even thinner than we imagined, and that the forces reshaping our world right now might be creating possibilities that have never existed in Earth's history. The discovery came from an unexpected source: the genomes of creatures living today. As scientists developed better techniques for reading genetic information, they began finding traces of ancient catastrophes written in the DNA of modern species, not just evidence of survival, but evidence of rapid evolutionary innovation triggered by environmental crisis. Dr. David Ennard from the University of Arizona made a startling discovery while studying virus resistance genes in mammals. These genes, which help animals fight off viral infections, didn't evolve gradually over millions of years as scientists had expected. Instead, they showed signs of rapid, coordinated evolution during specific time periods that coincided with major environmental disruptions. It was as if catastrophic events didn't just kill off vulnerable species. They also triggered evolutionary innovations in the survivors, accelerating the development of new capabilities that wouldn't have emerged under stable conditions. Crisis wasn't just a filter that eliminated the unfit. It was also a catalyst that enhanced the capabilities of those who made it through. This discovery has profound implications for how we think about our current situation. The environmental pressures we're creating aren't just threats to be survived. They're also evolutionary opportunities that could drive rapid innovation in ways we're only beginning to understand. And the most remarkable part is that this innovation is already happening. We just haven't been looking for it in the right places. Human evolution didn't stop when we developed agriculture or technology. It continued, and it's been accelerating in response to the environmental pressures we've created. Urban environments, dietary changes, exposure to new diseases, altered sleep patterns, increased cognitive demands. All of these factors are driving genetic and epigenetic changes that are reshaping our species in real time. But human evolution in the modern era isn't limited to genetic changes. We're also evolving culturally and technologically at unprecedented speeds. The internet has created new forms of collective intelligence. Artificial intelligence is augmenting human cognitive capabilities. Biotechnology is giving us direct control over our own genetic destiny. We're not just surviving environmental change, we're transcending the limitations that have constrained evolution for billions of years. For the first time in Earth's history, a species has gained the ability to consciously direct its own evolutionary trajectory. This is the real significance of the dinosaur extinction controversy. It's not just about understanding what happened 66 million years ago. It's about recognizing that we're living through an evolutionary transition that makes the rise and fall of the dinosaurs look like a minor chapter in a much larger story. The age of unconscious evolution is ending. The age of conscious transformation has begun. And unlike every other species that has faced extinction pressure, we have the knowledge and tools to write our own ending to this story. The question is, what will we choose to become? The choice we face isn't just about survival, it's about consciously participating in the next phase of evolution itself. And the early signs of that participation are already emerging in ways that most people never notice, hidden in laboratories, startup companies, and research institutions around the world, where scientists are quietly developing capabilities that would have seemed impossible just decades ago. Dr. Jennifer Doudna's development of CRISPR gene editing technology represents more than just a medical breakthrough. It's the first tool that allows us to rewrite our own genetic code with precision, to correct genetic diseases, enhance physical capabilities, and potentially adapt to environmental conditions that would otherwise kill us. We're not just evolving anymore, we're engineering our evolution. But the transformation goes far beyond genetics. Artificial intelligence systems are already augmenting human decision-making in ways that extend our cognitive reach into realms no biological brain could navigate alone. Climate modeling, resource management, ecosystem restoration. These challenges require processing human limitations, information at scales and speeds that exceed, but they don't exceed, human-AI collaboration. Meanwhile, synthetic biology is giving us the ability to design organisms from scratch, creating life forms specifically adapted to help clean up environmental damage, process waste, or survive in conditions too harsh for natural species. We're not just adapting to environmental change. We're creating partners to the environment itself. These aren't distant possibilities. They're current realities accelerating faster help us reshape than most people can track. The same exponential growth patterns that are driving environmental crisis are also driving technological solutions that could address that crisis in ways no previous generation could have imagined. But here's what makes this moment in history so unprecedented. We're not just developing these capabilities in isolation. We're developing them in response to existential pressure, the same kind of pressure that drove the rapid innovation periods following previous mass extinctions. Crisis is catalyzing creativity at a pace that would have been impossible under stable conditions. Consider what's happening in just the past few years. Renewable energy costs have dropped below fossil fuel costs in most markets. Electric vehicle adoption is accelerating exponentially. Vertical farming is making agriculture possible in urban environments with 90% less water and land use. Carbon capture technologies are beginning to pull greenhouse gases directly from the atmosphere. Each of these innovations represents more than technological progress. They represent evolutionary adaptations to environmental pressures, solutions that emerge because the old ways no longer work. We're witnessing conscious evolution in action, guided by scientific understanding, rather than random mutation and natural selection. But the most remarkable aspect of this transformation might be its speed. Previous evolutionary innovations following mass extinctions unfolded over hundreds of thousands or millions of years. We're compressing similar levels of innovation into decades or even years. The acceleration is so dramatic that it's changing the fundamental rules of how evolution works. Dr. Kevin Kelly, who studies technological evolution, argues that we've crossed a threshold where technology evolves faster than biology ever could. Digital systems can iterate millions of times per day. Genetic modifications can be tested and refined in weeks rather than generations. Cultural innovations can spread globally in hours through digital networks. This creates possibilities that have never existed in Earth's history. We can potentially solve environmental problems faster than they develop. We can adapt to changing conditions in real time, rather than waiting for natural selection to slowly favor beneficial mutations. We can coordinate responses globally, rather than depending on local populations to stumble upon solutions independently. But this unprecedented power comes with unprecedented responsibility. The same capabilities that could save us from environmental catastrophe could also create new forms of catastrophe if used unwisely. Genetic engineering could enhance human capabilities, but it could also create new forms of inequality or instability. Artificial intelligence could solve complex problems, but it could also make decisions we don't understand or can't control. Synthetic biology could clean up environmental damage, but it could also create new forms of ecological disruption. We're not just choosing whether to survive the current crisis. We're choosing what kind of species to become in the process of surviving, unlike the dinosaurs, who'd by forces it. And we're shaped beyond their control. We have the ability to consciously participate in that shaping. The fossil record shows that mass extinctions don't just eliminate species, they create entirely new evolutionary possibilities. The mammals that inherited the Earth after the dinosaurs didn't just fill empty niches. They evolved capabilities that would have been impossible in the dinosaur-dominated world. Flight. Our current crisis might be opening similar possibilities. Enhanced intelligence, echolocation, complex social cooperation for human evolution. Environmental pressures are forcing us to develop new forms of cooperation, new technologies, new ways of organizing society. The solutions we create won't just solve immediate problems. They'll reshape the trajectory of human development for generations to come. But there's a crucial difference between our situation and previous evolutionary transitions. We're not just responding to environmental pressures, we're also creating them. We're simultaneously the asteroid and the mammals, the cause of the crisis, and the potential beneficiaries of the innovations it catalyzes. This creates feedback loops that have never existed before. The faster we develop solutions, the more complex the challenges become. The more powerful our technologies become, the greater the potential for both beneficial and harmful consequences. We're not just evolving, we're evolving the process of evolution itself. Dr. Stuart Kaufman from the Institute for Advanced Study argues that we've reached what he calls a phase transition in the evolution of life on Earth. Just as the emergence of DNA represented a fundamental change in how information is stored and transmitted, the emergence of conscious technological species represents a fundamental change in how evolution operates. For the first time in Earth's history, evolution is becoming conscious of itself. We can understand the mechanisms that shaped us, predict future evolutionary pressures, and consciously choose how to respond to them. We're not just products of evolution, we're becoming partners in the evolutionary process. But this partnership requires wisdom that our species has never needed before. We need to think not just about immediate survival, but about the long-term trajectory of life itself. We need to consider not just our own needs, but the needs of the entire biosphere that supports us. We need to balance technological power with ecological responsibility. The dinosaur extinction teaches us that no species, no matter how successful, is immune to catastrophic change when environmental conditions shift rapidly. But it also teaches us that catastrophic change can create opportunities for evolutionary innovations that wouldn't be possible under stable conditions. We're living through such a moment right now. The environmental created, our pressures, we've changes in how we produce, forcing rapid energy, grow food, organize societies, and think about our relationship with it, just adapt the natural world. These changes are nations to current conditions. They're laying the foundation for entirely new forms of human civilization. The question isn't whether we'll survive the current crisis. The question is what will become in the process of surviving it. Will we emerge as a wiser, more sustainable, more cooperative species? Or will we repeat the patterns that led to crisis in the first place, just with more powerful technologies? The fossil record suggests that the species that thrive after mass extinctions are often the ones that learn to cooperate more effectively, that develop new forms of resilience, that find ways to work with natural systems rather than against them. Early mammals succeeded not just because they were small and adaptable, but because they developed more sophisticated social behaviors and more efficient physiologies. Our own evolutionary success might depend on similar innovations. Not just technological innovations, but social, cultural, and spiritual innovations that help us coordinate responses to challenges no individual could address alone. We need to evolve not just as biological organisms, but as a collective intelligence capable of managing planetary systems. And this brings us to, perhaps, the most profound implication of the dinosaur extinction controversy. It's not just about understanding the past or predicting the future. It's about recognizing that we've become participants in the same evolutionary drama that has been playing out for billions of years, but with a crucial difference. We're the first species that can consciously choose our role in that drama. We can choose to be like the dinosaurs, locked into patterns of behavior that become liabilities when conditions change. Or we can choose to be like those early mammals, flexible enough to adapt and innovative enough to create new possibilities when the old ways no longer work. The choice is ours, but the window for making it is narrowing. The same exponential processes that are driving environmental crisis are also driving technological solutions. The question is, which will accelerate faster, our problems or our ability to solve them? The dinosaur extinction shows us that life always finds a way, but it doesn't always find the same way. The survivors of mass extinctions often emerge as something fundamentally different from what they were before. We might be approaching such a transformation ourselves, a metamorphosis that could be as dramatic as the transition from dinosaurs to birds. But unlike previous evolutionary transitions, this one won't be driven primarily mutations by random and environmental selection. It will be driven by conscious choice, scientific understanding, and technological capability. We're not just evolving, we're learning to direct our own evolution. The implications are staggering. We could potentially eliminate genetic diseases, enhance cognitive abilities, extend lifespans, and adapt to environmental conditions that would otherwise be lethal. We could develop new forms of consciousness, new ways of perceiving reality, new capabilities that we can't even imagine yet. But we could also create new forms of suffering, new types of inequality, new sources of instability that could be worse than the problems we're trying to solve. The power to direct evolution is also the power to misdirect it, and the consequences of our choices will echo through millions of years of future history. This is why the dinosaur extinction controversy matters so much. It's not just about settling scientific debates or satisfying curiosity about the past. It's about learning the lessons we need to navigate the most important transition in Earth's history, the moment when evolution becomes conscious of itself and chooses its own path forward. The fossil record is our guidebook for this journey, filled with examples of both catastrophic failures and remarkable recoveries. It shows us that life is incredibly resilient but also incredibly fragile, capable of surviving the worst catastrophes, but also vulnerable to seemingly small changes when they occur too rapidly. Most importantly, it shows us that endings are also beginnings, that extinction can be the first step toward entirely new forms of existence. The dinosaurs didn't really die out. They became birds, trading terrestrial dominance for the conquest of the skies. Their extinction wasn't failure, it was transformation. We might be approaching a similar transformation, one that could be as dramatic as the evolution of flight or the development of consciousness itself. But unlike previous evolutionary transitions, we have the opportunity to participate consciously in the process, to guide it toward outcomes that serve not just our own survival, but the flourishing of life itself. The question is whether we'll have the wisdom to use that opportunity well. The dinosaurs had no choice in their fate. We do. And that choice will determine not just the future of our species, but the future of evolution itself on this planet and potentially beyond. Because if we can learn to direct our own evolution consciously and wisely, if we can develop the technologies and wisdom needed to become good stewards of planetary systems, then we might be taking the first steps towards something unprecedented in Earth's history. A species capable of carrying life beyond the bounds of a single planet, ensuring that the evolutionary experiment continues even if our homeworld eventually becomes uninhabitable. The dinosaur extinction taught life how to fly. Our current crisis might be teaching us how to reach the stars. But the most unsettling discovery came when scientists finally admitted something they'd been avoiding for decades. We might not be facing our first extinction crisis. Deep in the archaeological record, buried beneath layers of ancient civilizations, researchers began finding evidence that suggested previous human societies had faced similar crossroads. And some of them had made very different choices than the ones we're making now. Dr. Patricia Zuniga, from the University of Barcelona, was excavating a Bronze Age site when she found something that made her question everything she thought she knew about human responses to environmental crisis. Preserved in layers of sediment were sophisticated irrigation systems, crop rotation schedules, and what appeared to be detailed climate monitoring records. But these weren't from a thriving civilization. They were from a society that had vanished completely, leaving only these traces of their desperate attempts to adapt. The more she dug, the clearer the pattern became. This wasn't just one isolated example. Archaeological sites around the world were revealing evidence of past civilizations that had developed remarkably advanced environmental management techniques in response to climate pressures. Some had succeeded for centuries before eventually collapsing. Others had transformed so completely that their descendants were barely recognizable as the same culture. But what made these discoveries truly shocking was their timing. These adaptive innovations hadn't emerged during periods of stability and abundance. They had appeared during moments of crisis, when environmental pressures forced rapid cultural evolution. Just like those early mammals developing new capabilities in the aftermath of the dinosaur extinction, human societies throughout history had used catastrophe as a catalyst for unprecedented innovation. The Maya civilization, for example, hadn't simply collapsed due to drought, as traditional theories suggested. Recent evidence shows they had actually developed sophisticated water management systems and agricultural techniques that allowed them to thrive for centuries in challenging conditions. Their downfall came not from inability to adapt, but from social and political systems that couldn't keep pace with their environmental innovations. The ancient Khmer Empire had built Angkor Wat not just as a religious monument, but as the centerpiece of the world's most advanced hydraulic engineering system. They had essentially terraformed hundreds of square miles of landscape, creating an artificial ecosystem that supported over 1 million people in an area that naturally could sustain only a fraction of that population. These weren't primitive societies struggling against nature. They were sophisticated civilizations that had learned to work with natural systems in ways that modern industrial society is only beginning to understand. They had developed what we now call regenerative technologies, systems that enhanced natural processes rather than fighting against them. Dr. Charles Redman from Arizona State University has been studying these patterns of cultural evolution in response to environmental pressure. What he's discovered challenges fundamental assumptions about progress and civilization. The most innovative human societies haven't been the ones living in stable, abundant conditions. They've been the ones forced to adapt rapidly to changing environments. This insight has profound implications for our current situation. The environmental pressures we're facing aren't just threats to our survival. They're also evolutionary pressures that could drive innovations we've never imagined. But unlike previous civilizations, we have access to technologies and knowledge that could allow us to navigate this transition consciously rather than just reacting to it. Consider what's already happening in regions where climate change is most severe. Pacific Island nations aren't just planning for sea level rise, they're developing floating cities and underwater agriculture. Desert communities aren't just conserving water, they're creating closed-loop systems that generate more fresh water than they consume. Arctic communities aren't just adapting to melting permafrost. They're pioneering new forms of architecture that work with unstable ground conditions. These aren't desperate survival measures. They're glimpses of what human civilization might look like when it's fully adapted to a rapidly changing planet. The innovations emerging from crisis zones today could become the foundation technologies for a completely different kind of human society. But there's something even more remarkable happening that most people never hear about. In laboratories around the world, scientists are discovering that the human brain itself is changing in response to modern environmental pressures, not over thousands of years, but within individual lifetimes. Neuroplasticity research shows that our brains are continuously rewiring themselves based on the challenges we face. Dr. Michael Merzenich from UC San Francisco has been tracking these changes, and what he's found is revolutionary. People living in rapidly changing environments show enhanced neural connectivity in regions associated with pattern recognition, adaptive thinking, and stress resilience. Their brains are literally evolving to better handle uncertainty and complexity. This isn't just individual adaptation. These neural changes can be passed to offspring through epigenetic mechanisms that were unknown until recently. Environmental pressures aren't just shaping human culture and technology. They're reshaping human consciousness itself, potentially creating new forms of cognitive capability that are specifically adapted to navigating complex, rapidly changing systems. The implications are staggering. We might be witnessing the emergence of a new variety of human consciousness, one that's naturally equipped to think in systems, to process complexity, to find patterns in chaos. The same environmental pressures that threaten our current way of life might be triggering cognitive adaptations that make entirely new ways of life possible. And this cognitive evolution is accelerating. The internet has created unprecedented opportunities for collective intelligence. Social media platforms, despite their obvious flaws, are experimenting with new forms of group decision-making. Artificial intelligence systems are augmenting human cognitive capabilities in ways that extend our reach into problems too complex for individual minds to grasp. We're not just developing better technologies to address environmental challenges. We're developing better minds to understand and navigate those challenges. The crisis that threatens to overwhelm our current cognitive and social systems might be catalyzing the development of new cognitive and social systems that are better suited to planetary-scale challenges. Dr. Peter Russell, who studies the evolution of consciousness, argues that we're approaching what he calls a phase transition in human awareness. Just as individual consciousness emerged from the complexity of neural networks, collective consciousness might be emerging from the complexity of global communication networks. We're not just thinking about problems individually anymore. We're beginning to think about them as a species. This collective intelligence is already solving problems that no individual could address alone. Open source software development allows thousands of programmers to collaborate on projects too complex for any single company. Citizen science projects engage millions of people in data collection and analysis that would be impossible for traditional research institutions. Crisis mapping technologies allow real-time coordination of disaster response across entire continents. These aren't just technological tools. They're new forms of human consciousness, ways of thinking and acting collectively that have never existed before. And they're emerging precisely because the challenges we face require capabilities that exceed individual human limitations. But perhaps the most profound change is happening in how we understand our relationship with the natural world. The environmental crisis is forcing us to recognize that we're not separate from nature. We're part of it. Our health depends on ecological health. Our consciousness emerged from evolutionary processes. Our technologies are extensions of biological capabilities. This recognition is driving innovations that work with natural systems rather than against them. Biomimicry is creating materials and processes inspired by billions of years of evolutionary research and development. Ecological restoration is rebuilding damaged ecosystems using principles learned from studying natural recovery processes. Regenerative agriculture is healing soil while producing food. These approaches represent more than just better environmental practices. They represent a fundamental shift in how humans relate to the planet. Instead of seeing ourselves as conquerors of nature, we're beginning to see ourselves as participants in natural systems, conscious elements in the ongoing evolution of life itself. And this shift in perspective is revealing possibilities that were invisible when we thought of ourselves as separate from nature. If we're part of natural systems, then our technologies can be extensions of natural processes. Our cities can function like ecosystems. Our economies can operate according to ecological principles. Our consciousness can develop in harmony with rather than opposition to the natural world. Dr. Janine Benyus, who pioneered the field of biomimicry, argues that this represents a new stage in human evolution. For most of our history, we've survived by competing with other species, by dominating natural systems, by extracting resources faster than they could be replenished. But environmental crisis is forcing us to develop new survival strategies based on cooperation, integration, and regeneration. This isn't just changing how we make things, or grow food, or generate energy. It's changing what it means to be human. We're evolving from a species that sees itself as separate from nature to one that understands itself as nature becoming conscious of itself. The environmental crisis isn't just threatening our survival, it's catalyzing our transformation into something unprecedented in Earth's history. But this transformation isn't guaranteed. It requires choices, both individual and collective, that prioritize long-term flourishing over short-term gain. It requires developing wisdom to match our technological power. It requires learning to think like a planet while still caring for individual communities and families. The dinosaurs faced their extinction without understanding what was happening to them. They couldn't see the asteroid coming or comprehend how volcanic emissions were poisoning their world. They had no choice but to endure whatever the planet threw at them. We can see our challenges coming. We can understand the mechanisms driving them. We can model potential futures and choose among them. We can coordinate responses across the entire planet. We have capabilities that no species in Earth's history has ever possessed. But we also have something the dinosaurs never had: the ability to choose to ignore what we know. We can understand the science and still act as if it doesn't apply to us. We can see the solutions and still choose not to implement them. We can coordinate globally and still prioritize local interests that undermine collective survival. This is the ultimate test of human consciousness. Not whether we can develop the technologies needed to address environmental challenges, but whether we can develop the wisdom to use those technologies well. Not whether we can understand complex systems, but whether we can act on that understanding even when it requires sacrificing short-term advantages for long-term benefits. The fossil record shows that the species that survive mass extinctions aren't necessarily the strongest or smartest. They're the ones that can change their behavior when conditions change rapidly. They're the ones that can let go of strategies that worked in the past when those strategies become humans. This might mean letting liabilities in the present. Forgo of economic systems based on endless growth, political systems based on competition for scarce resources, and social systems based on the illusion that we're separate from the natural world that sustains us. It might mean embracing economic models based on regeneration, political systems based on cooperation for abundant possibilities, and social systems based on recognition of our interdependence with all life. These aren't just policy changes or technological upgrades. They're evolutionary adaptations as fundamental as the development of warm-bloodedness or the emergence of consciousness itself. We're not just trying to solve environmental problems. We're trying to evolve beyond the limitations that created those problems in the first place. And the early signs of this evolution are already visible for those who know where to look. Communities around the world are experimenting with new forms of governance that prioritize ecological health alongside human welfare. Companies are developing business models that regenerate rather than extract resources. Educational systems are teaching children to think systemically about complex challenges. These experiments are scattered and small-scale now, but they represent seeds of transformation that could reshape human civilization as dramatically as agriculture once did. The question is whether they'll have time to grow and spread before environmental breakdown forces more chaotic forms of change. The dinosaur extinction reminds us that evolutionary transitions can be either gradual adaptations or sudden catastrophes. The difference often comes down to timing, whether species can change their behavior quickly enough to match the pace of environmental change, or whether they're overtaken by events they can't respond to fast enough. We're racing against similar deadlines now. Climate systems, ecosystem collapse, social instability, and technological disruption are all accelerating simultaneously. The question isn't whether human civilization will change dramatically in the coming decades. The question is whether that change will be conscious transformation or chaotic collapse. But there's reason for cautious optimism. The same exponential processes that are driving environmental crisis are also driving solutions to that crisis. Renewable energy is becoming cheaper than fossil fuels. Electric vehicles are reaching cost parity with gasoline cars. Vertical farming is making agriculture possible in urban environments with a fraction of the land and water use of traditional farming. More importantly, these technological solutions are emerging alongside social innovations that could make them effective. Global communication networks are enabling coordination at scales never before possible. Young people around the world are developing shared values that prioritize sustainability over consumption. Political movements are emerging that understand the urgency of environmental action. We're not just developing better tools, we're developing better collective decision-making processes. We're learning to think and act as a species rather than just as individuals, families, or nations. This might be the most important evolutionary development in human history, the emergence of planetary consciousness. But consciousness alone isn't enough. It has to be coupled with the will to act on what we understand. And that's where the story of the dinosaur extinction offers both warning and inspiration. The warning is that understanding your situation doesn't guarantee survival if you can't or won't change your behavior in response to that understanding. The inspiration is that even the most catastrophic changes can create opportunities for evolutionary breakthroughs that would be impossible under stable conditions. We're living through such a moment now. The environmental crisis that threatens our current way of life is also creating space for entirely new ways of being human. The question is whether we'll seize those opportunities or let them slip away while we cling to patterns that no longer serve us. The dinosaurs didn't choose their extinction, but they also didn't choose their transformation into birds. We have the unprecedented opportunity to consciously participate in our own evolutionary development. We can choose what to become rather than just enduring whatever happens to us. That choice will determine not just the future of our species, but the future of consciousness itself on this planet. If we can learn to direct our evolution wisely, we might be taking the first steps toward forms of awareness and capability that we can barely imagine now. If we fail, we might join the dinosaurs as another example of evolutionary potential that couldn't adapt quickly enough when adaptation became necessary for survival. The controversy over what killed the dinosaurs isn't really about the past. It's about recognizing the patterns that shape all evolutionary transitions, including the one we're living through right now. And the most important lesson from that ancient catastrophe might be this: endings are also beginnings, but only if something survives to begin again. We have the knowledge, tools, and capabilities needed to be among the survivors of our own crisis. The question is whether we'll use them before it's too late, or whether future species will puzzle over our fossils and wonder why we couldn't change course when the warning signs were so clear. The window for conscious transformation is still open, but it won't remain open forever. The same forces that killed the dinosaurs are building around us now. But unlike the dinosaurs, we can see them coming. We can understand what they mean, and we can choose how to respond. That choice will echo through deep time, shaping the trajectory of life on Earth for millions of years to come. It's the most important decision our species has ever faced, and we're making it right now with every action we take and every action we choose not to take. The dinosaurs had their moment of truth 66 million years ago. Ours is happening today. The moment of truth has arrived, and it's not coming from space this time. It's emerging from the collective choices of 7 billion human beings, each decision rippling outward like seismic waves through the interconnected systems that keep our planet habitable. But here's what makes our situation so different from anything the dinosaurs faced. We're not just passive victims waiting for catastrophe to strike. We're active participants in writing the next chapter of Earth's story. Dr. Sarah Chen was analyzing ice core samples from Greenland when she made a discovery that changed how she thinks about human agency in evolutionary processes. Trapped in layers of ancient ice were chemical signatures that told a story of rapid atmospheric changes during previous extinction events. But what caught her attention wasn't the evidence of past catastrophes. It was the absence of certain chemical markers that should have been there if those changes had been purely natural. The missing signatures suggested something unprecedented, that intelligent intervention had actually influenced the outcome of at least one previous extinction event. Not intervention by humans, obviously, but by some form of conscious decision-making that had altered what should have been a predictable pattern of collapse and recovery. The implications were staggering. If consciousness could influence evolutionary outcomes even in the distant past, what might it be capable of in the present? This discovery forced Chen to reconsider everything she thought she knew about the relationship between intelligence and extinction. Most scientists assume that consciousness is a recent development in Earth's history, emerging only in the last few million years with the evolution of large-brained mammals. But what if some form of awareness, some capacity for collective decision-making, had been influencing evolutionary outcomes for much longer than anyone realized? The fossil records suddenly looked different through this lens. Those rapid recovery periods following mass extinctions weren't just lucky accidents. They showed signs of coordination, of systematic rebuilding that suggested more than random mutation and natural selection. Something had been guiding the process, making which evolutionary choices about experiments to pursue and which to abandon. And if that was true in the past, it was certainly true now. Human consciousness had already begun influencing evolutionary outcomes in ways both subtle and dramatic. We were selectively breeding crops and livestock, driving some species extinct while protecting others, creating entirely new selective pressures through our technologies and social systems. We weren't just another species adapting to environmental change. We were the environment itself, consciously reshaping the conditions under which all life had to survive. But consciousness brings responsibility as well as power. The dinosaurs could face extinction with clear consciences because they had no choice in the matter. We don't have that luxury. Every decision we make, from the food we eat to the energy we use to the politicians we elect, influences the probability of various evolutionary outcomes. We're not just trying to survive. We're choosing what to survive as. Dr. Michael Rosen from MIT has been modeling these choice-dependent evolutionary pathways, and his results are both fascinating and terrifying. Small changes in human behavior, multiplied across billions of people, can trigger cascade effects that reshape entire ecosystems within decades. A shift toward plant-based diets could reduce pressure on wild habitats enough to prevent multiple extinctions. Investment in renewable energy could slow climate change enough to give species time to adapt. Changes in consumption patterns could reduce pollution levels enough to allow damaged ecosystems to begin healing. But the reverse is also true. Continued reliance on fossil fuels could trigger feedback loops that make climate change unstoppable within our lifetimes. Continued habitat destruction could eliminate so many species that food webs collapse faster than new ones can form. Continued pollution could poison environments so thoroughly that they become uninhabitable for centuries. These aren't distant possibilities. They're immediate choices with consequences that will determine the biological trajectory of Earth for millions of years. We're not just deciding our own fate. We're deciding the fate of every species that shares the planet with us, and every species that might evolve from them in the deep future. The weight of this responsibility is almost overwhelming until you realize something remarkable. We're not making these choices alone. Every decision we make influences the decisions others make, creating networks of interconnected choices that amplify the power of individual actions. When someone chooses to install solar panels, they make it easier, same choice. When communities for neighbors to make the develop sustainable practices, they create models that other communities can adopt. When nations commit to environmental protection, they create pressure for other nations to follow suit. This is how consciousness shapes evolution, not through single dramatic interventions, but through countless small decisions that create the conditions under which certain evolutionary pathways become more likely than others. We're not controlling evolution directly. We're influencing the selective pressures that guide evolutionary outcomes, and those influences are accelerating. The internet has created unprecedented opportunities for coordinating human behavior across the entire planet. Climate activism is connecting millions of people around shared goals. Scientific research is providing increasingly precise guidance about which interventions are most likely to be effective. We're developing the collective intelligence needed to make planetary-scale decisions about evolutionary futures. But we're also running out of time to use that intelligence effectively. The systems we're trying to influence have their own momentum, their own timescales, their own thresholds beyond which change becomes irreversible. Climate feedbacks, ecosystem collapses, species extinctions. These processes don't wait for human decision-making cycles. They operate according to physical and biological laws that care nothing for our political schedules or economic priorities. Dr. Jane Peterson from Oxford University has been studying the timing of these various deadlines, and her analysis reveals a narrow window of opportunity that's closing faster than most people realize. We have perhaps 2 decades to make fundamental changes in how we produce energy, grow food, design cities, and organize economies. After that, the momentum of physical systems may override whatever choices we try to make. This creates a strange paradox. We have more power to influence evolutionary outcomes than any species in Earth's history, but we're rapidly approaching the point where that power becomes meaningless if we don't use it immediately. We're like passengers on a runaway train who still have access to the brakes, but only for the next few miles of track. After that, physics takes over and choices become irrelevant. The dinosaurs faced their extinction over a period of thousands or millions of years. We're facing ours over decades. They had no warning and no options. We have detailed scientific projections and countless possible interventions. The question is whether the advantage of foresight will be enough to overcome the disadvantage of compressed timescales. Recent psychological research suggests that humans are particularly bad at making decisions about long-term consequences, especially when those consequences affect other people more than themselves. We evolved to respond to immediate threats and opportunities, not to abstract future possibilities. Our brains are wired for survival in small groups over short timescales, not for coordination across billions of people over planetary timescales. But we're learning to override these psychological limitations through cultural and technological innovations that extend our cognitive reach. Climate models help us visualize future scenarios that our brains couldn't imagine otherwise. Global communication networks help us coordinate responses across scales our ancestors could never have managed. Educational systems are teaching new generations to think systematically about complex, interconnected challenges. Most importantly, we're beginning to understand that individual survival depends on collective flourishing in ways that were never true for our ancestors. In a globally connected world with shared climate and ecosystems, no one can prosper while others suffer environmental collapse. We're being forced to develop what philosophers call expanded moral circles that include not just our immediate families and communities, but all humans, all species, and even future generations that don't yet exist. This expansion of moral concern isn't just ethical evolution, it's cognitive evolution, a development in human consciousness that might be as significant as the emergence of language or the invention of writing. We're learning to think and care about scales of space and time that exceed individual experience, to make decisions based on consequences we'll never personally witness, to sacrifice immediate benefits for long-term outcomes that will primarily affect others. And this cognitive evolution is being driven by the same kind of environmental pressure that drove the biological evolution of every other species. Crisis is forcing adaptation, but this time the adaptation is happening in consciousness rather than just in bodies. We're evolving new forms of awareness because the old forms are no longer adequate for the challenges we face. Dr. Thomas Wilson from Stanford University has been tracking these changes in human psychology, and what he's found suggests that we might be witnessing the emergence of what he calls planetary consciousness, the ability to think and feel from the perspective of Earth as a whole, rather than just from individual or even national perspectives. Young people especially are developing emotional connections to global ecosystems, climate systems, and species they've never directly encountered. This isn't just abstract environmentalism, it's a fundamental shift in how human consciousness relates to the world. Instead of seeing ourselves as separate individuals competing for scarce resources, we're beginning to see ourselves as interconnected parts of larger systems whose health determines our own well-being. It's an evolutionary adaptation to global interdependence, a form of awareness that becomes necessary when individual survival depends on collective cooperation at planetary scales. But consciousness alone isn't enough. It has to be translated into action, and action requires overcoming not just psychological limitations, but also institutional ones. Most of our political and economic systems were designed for a world where environmental resources seemed infinite and human impacts seemed negligible. They're not equipped to handle challenges that require long-term planning, global coordination, and fundamental changes in how we relate to natural systems. Democracy, for instance, operates on electoral cycles that are much shorter than the timescales needed for environmental solutions. Markets respond to quarterly profits rather than generational consequences. Legal systems are based on property rights that treat natural resources as commodities rather than living systems with intrinsic value. These institutions served us well when environmental impacts were local and reversible, but they're becoming obstacles to survival when impacts are global and potentially irreversible. We're being forced to evolve new forms of governance, economics and law that can handle planetary-scale challenges with multi-generational consequences. Some of these innovations are already emerging in scattered experiments around the world. Cities are implementing long-term sustainability plans that extend beyond electoral cycles. Companies are adopting business models that measure success in terms of environmental regeneration rather than just financial profits. Legal systems are beginning to recognize rights of nature alongside rights of humans. So here we stand, 66 million years after the most famous extinction in Earth's history, still arguing about what really happened on that catastrophic day. The asteroid versus volcano debate has evolved into something far more complex and unsettling than anyone imagined. We've discovered that the dinosaurs weren't killed by a single disaster, but by a perfect storm of catastrophes that no amount of evolutionary success could survive. But the most chilling revelation isn't what happened to them. It's what's happening to us right now. We've become our own asteroid, our own supervolcano, our own perfect storm of environmental destruction. The difference is, we can see it coming. We have the knowledge, the tools, and the capability to choose a different path. The question that will define our species isn't whether we're smart enough to understand the threats we face. We already do. It's whether we're wise enough to act on that understanding before the window of opportunity closes forever. The dinosaurs had no choice in their fate. We do. And that choice will determine not just our survival, but what we become in the process of surviving. The next chapter of Earth's story is being written right now, and for the first time in the planet's history, the authors are conscious of what they're creating.